Hello everyone. Today I will talk about our work on intention-aware robot crowd navigation with attention-based interaction graph. Let's begin with an introduction. Navigation in crowded spaces with other dynamic agents is a very important robotic problem. It has led to many real-world applications. Among all the challenges in crowd navigation, in this paper, we ask the following two questions. First, how to incorporate the future intentions of other agents in robot planning so that the robot is more proactively avoiding collisions. Second, how to effectively model different types of interactions that are happening in a dense and highly interactive crowd, and ideally in a principled way. Lots of previous work in crowd navigation has already made efforts toward this end, including reaction-based methods and learning-based methods. However, both methods usually fail to consider people's future intentions as well as all pairwise interactions into robot planning. This results in short-sighted robot behaviors such as the freezing robot problem. To deal with this issue, some methods have considered the prediction of human trajectories. However, they are usually constrained in discrete robot action space, or only consider a small and finite set of human intentions. We propose an intention-aware RL framework, which incorporates human trajectory prediction into a proactive robot decision-making process. Given the past M-step human trajectories, we can take any off-the-shelf trajectory predictor to predict the future trajectory for each human for k steps. And in our MDP formulation, the state includes the robot state W as well as the current and future states of all observed humans, U1 until UN. The action space is the desired velocity of the robot, and we assume that the state transition probability is unknown because the human dynamics is hard to model. To ensure that the robot proactively avoids the intended path of humans, we define a reward function so that the robot gets a positive reward if it gets closer or arrives at the goal. In contrast, the robot gets a negative penalty if it moves away from the goal or collides with the current or future human positions, as shown by the red circles. The darkness of the red color indicates the magnitude of the penalty. In our second contribution, we propose a novel graph neural network to effectively model the different interactions among the agents. We formulate the crowd navigation scenario as a spatial temporal graph, or ST graph. The figure below contains both spatial edges and temporal edges. The robot-human spatial edges model the robot-human interactions. The human-human spatial edges models the human-human interactions. We separate these two types of spatial edges because we only have control of the robot, not the humans. Finally, a temporal edge connects the entire graph between two adjacent time steps to model the change of the graph in the time axis. In order to learn the graphical model from data, we convert the ST graph to a vector graph so that each box is a function with parameters to be learned. Here's our policy network. We use two attention networks to represent the robot-human and human-human interactions, respectively. After we get the predicted human trajectories from the green trajectory predictor, we feed both the current and the future human positions into the HH attention network. It assigns attention weights to the features of each human with respect to other humans. Then we use the robot state as well as the weighted human features from the HH attention to give another weight on the human features with respect to the robot. Finally, all the weighted features are fed into a gated recurrent unit or GRU, which represents the temporal function. We train the policy network, which include the non-shaded part, with model-free RL. Then let's move on to experiments and results. In the simulation experiment, we observe that the ORCA baseline ends up with a collision. Because ORCA does not consider all the heterogeneous ST interactions, it also does not predict the human motions for more than one time step. An ablation of our model with no prediction is able to succeed. However, the robot occasionally intrudes into the future paths of other agents, resulting in an impolite behavior. Finally, our method enables a more proactive robot that is able to succeed with no intrusions. We also transfer the learned robot policy to a Turtlebot 2 as shown in the video. We obtain the robot and human positions from all onboard sensors. The success rate is around 83%. In all failure cases, the robot collides with walls during detour. Finally, limitations and future work includes handling the environmental constraints, as well as developing a hybrid policy using motion primitives to improve the training efficiency for RL. That's all. Thank you for listening.